Hey there, we're going to take a look at the first in our chapter 5 series here that has to do with dealing with forces that are not meeting together, nice single straight lines, sort of getting a little bit more realistic, but, we're still going to be doing relatively simplified versions of this. So we've dealt with forces that are meeting head to head or they're tail to tail, something along those lines. But now we're going to be dealing with those cases where forces are coming together at some funky angle, right? And all different kinds of things, not just right angles to it. So we're going to teach some different techniques in here to deal with this. Some of these are called vector components, is a big part of this, which sounds scarier than it is. We're going to use Sohcahtoa a lot. And then we'll be talking about two specific examples of applications of forces that are applied at angles, specifically taking a look at friction forces, and then also taking a look at inclined planes. Those are going to come up later on in this series. This particular video right here is really just about reviewing some of our basics that have to do with adding vectors together and some of our basic Sohcahtoa trigonometry kinds of things. So going along with that, I know you guys have some experience with dealing with different kinds of, this one I want pen right there, give me my pen, with different types of vectors. So you guys know this, if we add net forces together, we have to remember to add them tip to tail. And this is important to make sure that we're adding them together and lining them up in a way that makes sense in terms of the vector notation. So number one's a really easy one. If we have two vectors that are 10 newtons to the right, and then, another 5 newtons to the right, 10 and 5, that's a pretty easy one to add. When we draw our resultant vector, which kind of shows the results of adding those two things together, it's pretty easy when we draw it. We start at the beginning, the tail of the first vector, and we end at the end, which is the tip of the last vector. So that would be our resultant vector, which would also be our net force vector, and it would simply be equal to 15 newtons. No big deal, pretty straightforward. When we're starting to do vectors at different directions, though, this gets a little bit trickier. So if you take a look at what's happening in number 2, we've got two different vectors now going in different directions. 10 newtons down, maybe something like that, 10 newtons, and then 5 newtons up, which would be this way, right? 5 newtons this direction. So now when we're drawing a resultant vector, again, we have to kind of draw it the same way, but it's less clear. A lot of students want to draw it this way, kind of pointing up, like continuing, and that's not quite what we're doing here. Remember, resultant vectors start at the beginning, which was the tail of this first vector, and end at the end, which is the tip of the last vector. So our resultant vector is actually here, pointing downwards. And mathematically, it would make sense to do this. It's 10 newtons down, 5 newtons up. Our resultant vector should be down. That would make more sense. So we could write that as, say, -5, but it's 5 newtons in the downward direction, whatever we want to do there. And then let's take a look at this last one. Now we're going to start to kind of broach, well, what happens if they're not just in line? What do we deal with here? So here we've got a vector that's 10 newtons up, and now it's 5 newtons to the right, this way. And if I draw it, you can probably see kind of what a resultant vector is going to be, or maybe you can start to anticipate what it might be. When we draw this, again, we start at the beginning, the tail of the first vector, and we end at the end, which is the tip of our last vector. Our resultant vector here is a hypotenuse. You can kind of see that right angle here. So figuring out the length of our resultant vector is actually relatively straightforward. We can't just add, though. It's not 15. We're not just subtracting. Now we're using Pythagorean Theorem, right? 10 squared plus 5 squared would equal r squared. A squared plus b squared equals c squared. So again, when we have them at angles, we have to start to use a little bit more of our geometry and eventually our trigonometry skills. Figuring out this angle here that it's at, we can't just say it's up or down or kind of up and to the right. We kind of have to give a more specific angle to this. And that, again, would be using some of our trigonometry. Sohcahtoa, we'll come back to this here in a little bit. But we can figure out what that angle is using some fairly basic geometry, early geometry kind of skills. So again, adding vectors at an angle, simply a matter of practicing how do we draw what that resultant vector is. From the tail of the first vector to the end of the last vector, from beginning to end, basically is how we draw our resultant vectors. So I want to kind of do a quick little note on this one. When we're adding our vectors, doesn't matter which order we do it in. We did 10 newtons up and 5 newtons to the right. That's how we did that last one. 10 newtons up and 5 newtons to the right. But what happened if we added it together in a different order? So this was our resultant vector here. That was resultant right there. That was it. 10 up, 5 to the right. What if we added them together in a different order? Does that matter? Most of the time in physics, it does, right? We get super picky about it. But luckily for us, in this case, it doesn't magically. Just like in addition, the order of addition doesn't really make a difference, right? 3 plus 2 and 2 plus 3 are the same thing. Turns out, this is a useful fact for us, the order that we add our vectors in, we can kind of manipulate it to make our lives easier. So we could have done the 5 newtons to the right first, 5 newtons, and then done 10 newtons up. There it is right there, 10 newtons like that. If we did it this way, take a look at what the resultant vector is. My picture is going to be a little funky because, I'm not drawing super great, but take a look at what our resultant vector is. There it is. They're essentially the same vector. They should have the same length or magnitude, and they should be at basically the same angle. So if you take a look at this angle here, they're both pointing, well, I know my camera's a little bit off. They're both pointing up and to the right at basically the same angle. I know this angle here is not the same as this angle. They're added up to 90 degrees, but they're the same general angle to it. And actually, if I kind of did this imaginary vertical, that angle and this angle are the same thing. So luckily for us, we're going to take advantage of this, that the order that we add our vectors in terms of which one's first and which one's second, doesn't matter, as long as we keep the magnitude and direction of all of our vectors the same, and as long as we add them tip to tail, it doesn't matter which one comes first, second, or third in the order. That's a useful trick that we're going to use later on. Okay, some basic trigonometry coming back to the Sohcahtoa. I know you've kind of heard about this, but I just want to kind of review really quickly what Sohcahtoa means, just in case there may be a couple of you out here that don't know it or haven't practiced it in a long time. Basically, what Sohcahtoa has to do with is our sine, cosine, and tangent. So here means that the sine of an angle, we use the symbol theta to represent any angle. So if I want to say that this is my angle here, my triangle right here, that's my angle. If I take the sine of this angle, whatever it is, okay, again, enter it into a calculator, there is a basic geometric relationship to it, which would say that the opposite, or the length of the opposite leg divided by the length of the hypotenuse, is equal to the sine of that angle. That's what SO stands for, SOH. Sine of the angle is equal to the ratio of the opposite leg divided by the hypotenuse leg. The opposite is always one that's directly, literally across from the angle that we're measuring. So if this was our theta, this is the opposite angle. And then this leg that's touching the angle would be called the adjacent leg. And again, the right angle here is called the hypotenuse. And again, you have to have a right triangle for these relationships to work. If you have an acute, triangle that's, kind of one of these sorts of shapes, Sohcahtoa doesn't work in this sort of a triangle, or in the really obtuse kind of angles. It doesn't work in these kinds. You have to have a right angle triangle. Has to be one right angle in there for these to work. So to restate, sine of an angle equals the opposite of our hypotenuse. Ka right here means the cosine of angle of theta would be equal to the adjacent leg divided by the hypotenuse. And then the last one, toa, means that the tangent of any angle, of that angle, would be equal to the opposite over the adjacent sides. So again, these are ratios. Important thing to note, by the way, if you guys are using graphing calculators, if you're in advanced math classes, make sure that you are in degrees in your calculator. Make sure that you are not in radians. If you don't know what radians are, you're fine. If you do know what radians are, make sure to check that your calculator is in degrees and not in radians. This sometimes affects certain students depending on what their math enrollment is right now. So double check that if you're not sure to ask. And then we talked about the Pythagorean Theorem earlier, which is that a squared plus b squared equals c squared. We use these two rules all the time. So Sohcahtoa, Pythagorean Theorem, those are the things that we are going to depend on, rather than a bunch of really obscenely complicated trigonometric identities and ratios. This is all we need: Sohcahtoa and Pythagorean Theorem. That's going to get us everything that we need in this particular chapter. Last thing I'm going to mention in this particular unit is describing our angles. One of the things I want to point out is that when we are describing vectors, when we say, hey, head out for 10 miles, well, 10 miles, which direction, right? It's really important to say our directions in particular ways. There's some particular language we're going to use, because say, for example, this red vector up here, most students would say, yeah, head out for, for 10 miles northeast. Well, northeast means something very particular here. The term northeast would mean exactly 45 degrees. between north and east, exactly halfway. If we actually meant 50 degrees and you headed 10 miles, by the time you got to the end of that vector, you'd be a long ways from what your intended direction was supposed to be. And the further away you are from that 45-degree angle, that exact thing like this one over here, if you just said head out 10 miles, northwest, and you actually meant head out at 35 degrees, you're really going to have a lot of error in there. So here's the last piece I want to mention, how we describe our angles. Okay, it's a two-word description. We can't just say northeast. We're going to use the phrases north of east or east of north. I know it sounds really funny to say that. What the hell does that mean? North of east or east of north. So this particular angle right here, see where this 50 is labeled? This 50 is labeled between the east axis and somewhere in between. So that means we're actually going 50 degrees north of east. East is the main direction, and I'm rotating from there. This angle up here, if you remember, right degrees here is 90 degrees, right? So this angle here up in this spot's actually 40 degrees. This angle would be 40 degrees east of north. North is the main angle, and I'm turning east of there. This one over here, this one that's described as 35 degrees. Well, this is 35 degrees from which axis? Is it 35 degrees from north or 35 degrees from west? This particular one here is 35 degrees from west. And now it's north of west, not south of west. So this would be 35 degrees north of west. This being the main direction that you're heading, this is the turn direction. Am I turning 35 degrees to the north or 35 degrees to the south? So a couple other practice ones, because this is usually really awkward for students in terms of how they're doing it. See if you can practice doing these bottom two, the 65 and the 80. How would you describe those two angles using now our new coordinate language? Okay, this one right here, that's 65. Okay, our main direction is west, and I am turning to the south of that western direction. This would be 65 degrees south of west. This complementary degree right here, by the way, I think is it 15? Oh, 25. This complementary angle here would be 25 degrees, and that would be west of south. That's a little bit different. And then this one right here, this 80. Okay, how would we describe this 80 degrees? This is not 80 degrees east of south. This is 80 degrees south. Oh, sorry. South. I got to draw an S. South of east. There we go. So again, I'm going east. I'm turning 80 degrees south of east. Again, it's a little bit weird to figure out what this is. This angle right in here, that one would be 10 degrees east of south. See how they're complementary? Okay, they add up to 90 degrees, and you flip-flop the directions. So they can both be correct. You can either say 10 degrees east of south, or you could say 80 degrees south of east. Those describe the same vector, okay? So again, when we're describing resultant vectors and we're giving angles, not only is the angle degrees required, but the directionality of it is also required. If we're talking about compass rose, which is a common thing, you would give it with west of north. Sometimes we will say above horizontal or below horizontal, or to the right of vertical or to the left of vertical. So again, we have some other ways that we describe a resultance, not just the angle, but the directions to that angle, if that makes any sense at all. So there you go. Some basic reviews to adding vectors, remembering our tip to tail methods, how to draw resultant vectors, some review on what Sohcahtoa is, and now you can kind of see some of our relationships with describing degrees, okay? So here we go. We'll see you in the next video, which has a little bit more to do with actually applying these to forces. Okay, see you in the next one, guys. Bye.